Okay, shall we start? So welcome to this our last section. So we are gonna start with the jackpot, no interactive aggregatable lotteries, written by Niels Fleischacker, Matthias Hall Anderson, Mark Shimkin, and Benedict Wagner, and Niels will give a talk.
Yeah, thank you for the introduction. So yeah, this is joint work with Matthias, Mark, and Benedict. And so it's about a non-interactive aggregatable lotteries. So maybe we start with what even is a lottery supposed to be? Why do we want a lottery? And well, what is it supposed to do? So in a bunch of proof of stake based blockchain protocols, we have the problem that at regular intervals, we need to select from a large number of participants some small subset, a so-called committee that is supposed to then make some kind of decision. This can also happen in other scenarios, but it happens especially in those blockchains. And so we want this kind of protocol that basically is then supposed to select a committee of some size, roughly n over k, where n is just the number of total participants and k is some constant. And it should satisfy some properties that, for example, well, you cannot cheat to make yourself get selected more often than you should. So whatever you do, you should not be able to manage to get selected with probability more than 1 over k. Also, nobody else should be able to basically make you lose more often than you're supposed to. Basically, an honest participant should always be selected with probability of k. We also need to prevent different participants from essentially correlating the events of them winning the lottery. Because this would mean that you can basically have a bunch of malicious parties. They cannot increase their winning probability, but they can basically ensure that they will be selected at the same time. So whenever that happens, they have a good chance of having a majority in the committee, and they could then do some malicious behavior. So we want all of that. And then this is supposed to be a non-interactive, because obviously we could do this by just running a large MPC protocol among all of the participants, and then they could select a small committee. That works fine, but that would cost a lot of interaction, and interaction is very expensive in this kind of setting. So instead, we want a non-interactive lottery. So how do you do a non-interactive lottery? So in the Ethereum blockchain, what they're using is a lottery based on verifiable random function. So the verifiable random function that they're using is specifically that they use the unique BLS signature scheme. And after signing something, which they basically use as a verifiable unpredictable function, they then apply a random oracle to it, and then you have a verifiable random. And they use this verifiable random function. Everybody basically who wants to participate registers a public key and stores, of course, their own secret key. And whenever a lottery is supposed to take place, a seed magically appears in the sky. We do not really need to care where it comes from. It comes from the randomness beacon, but this is basically irrelevant for us right now. Basically, a seed appears. And what they do is they say, okay, so we just evaluate our VRF on this seed. And what that means is that you basically get the value of the VRF at this point, and you get a proof that this VRF indeed evaluates to X at this point. And now you win the lottery if the value that you get from your VRF is smaller than some threshold that is chosen to, well, coincide with the winning probability you're supposed to get. And so basically, when you win the lottery, you can then publish your tau j and your xj, and anybody can verify that you indeed won the lottery by just verifying that this is indeed the correct evaluation of your VRF, and that, of course, the xj you published is indeed smaller. Okay, this works fine. it is indeed the case here that nobody can basically force you to win with a smaller probability. You can also not cheat to win with a higher probability. The fact that you cannot correlate your winnings with other parties is not as straightforward, but it does work. However, it does have a problem. And this problem is that storing these winning tickets, as I said, you need to publish your tau and your X, and storing these winning tickets actually takes a lot of space, because every winning party of the of this lottery needs to publish these values, and this can be like 1,000 or 2,000 participants, and this takes a lot of space, and well, space is at a premium in these blockchain applications. So what we would like is if we could basically store something smaller than an individual winning ticket for everybody who wins the lottery. Okay, so how might we be able to do that? The first idea is that, well, we can actually switch maybe to a VRF that has a small codomain. So instead of using a VRF with a large codomain and using this threshold T to basically get our winning probability correct, let's say we have a codomain that's basically of size K, and now we can basically do the same thing, except that now we say you win if your xj hits some very specific value that is chosen independently for every individual person based on a random oracle. So you evaluate a random oracle on I, which is basically which lottery you're currently playing. So it's the first lottery, second lottery, ith lottery, and J, which is basically your identity, as well as the seed of the lottery. So you get an individual challenge, and if you manage to hit the challenge, then you win the lottery, which makes it much easier to argue about the fact that now actually there are no correlated winnings, because you now have completely independent challenges. So correlating your wins is basically. So this is already nice, because the fact that this xj is basically now publicly computable, so you can basically just derive it from public information, we already do not need to publish the xj at all. So you would only need to publish the tau j, which is already good, because, well, it cuts down by maybe 1/2 or 1/3 at least of the space that you need to store stuff. But it's even better if we would have a linearly homomorphic VRF. So if we would have a linearly homomorphic VRF, then you can imagine, okay, we have a bunch of these evaluations of the VRF. And normally we would need to store all of these taus, tau 1, tau 2, tau 3. And instead, if it's linearly homomorphic, what we can do is we can derive some weight T, and we can basically compute these linear combinations of the proofs of the X's and of the public keys. And this will verify exactly if all of these original proofs verify under their individual public keys. So that basically means that we could, instead of storing all the individual taus, the idea would be, well, we can store only this single value, which would mean that now the storage actually does not depend on how many people win the lottery. It's independent, it's a constant size. So that would be great. Unfortunately, we do not know of such VRFs. We do not know of any linearly homomorphic VRF with a small coding. So that is a bit of a problem. However, well, if we think about it, what is a VRF really other than a vector commitment for a very long random vector? So if you're willing to make a small concession where we say, okay, so with this VRF construction, you would be able to basically run an arbitrary number of lotteries with the same key. So if you're willing to make the concession that after a couple of hundred or a couple of thousand lotteries, you need to rekey your lottery, then we could use a vector commitment instead of using a VRF. So how would that work? Basically, every participant at the beginning would just choose a random vector and commit to this random vector using a vector commit. And then we basically do the exact same thing as before, except that instead of evaluating a VRF, we're now just opening the vector commitment at position I for the ith lottery. So this gives you an opening, tau ji for the jth participant in the ith lottery. And as before, we basically win if you manage to hit your individual challenge. So this is still the case, and it's still the case that you basically cannot cheat here, because you are not able to predict this value at the time when you make the commit, because it depends on the random seed, which will only be fixed whenever the lottery takes place. So once you've basically published this proof, anybody can then again take this xji that you get from the random oracle here and verify that your commitment, which now basically takes the part of the public key from before, actually verifies at the position I, so that it opens to xji at position I, and that this is a correct proof for that. So this is good. And we could now, if the vector commitment is linearly homomorphic, we could use the same idea as before, right? And the good thing is that we do actually know of linearly homomorphic vector commitments. Well, technically, we know of linearly homomorphic polynomial commitments, but we can use the polynomial commitment as a vector commitment by just committing to a polynomial that's basically set to evaluate to the correct values at the correct points. So most notably, KCG commitments can be used as a vector commitment and are linearly homomorphic. So that sounds good. The issue is that it still doesn't quite work. So it would probably work if you would define a lottery in a standalone setting. You would probably be able to prove that. The problem is that these lotteries are not run in a standalone setting. So these are composed with other lotteries that run at the same time or at different times. They're composed with other cryptographic protocols. So we do need composability for this protocol. And if we need composability, well, basically what we do is we define the security of the lottery in a universal composability framework. But if we do that, then in our proof, what we will need to do is we will need to equivocate commitments that we basically make ourselves. And at the same time, we need to extract from commitments that the adversary makes. And the problem is, that means that we require simulation extractability of the vector commitment. And, well, KCG commitments are not simulation extractable. And in particular, no linearly homomorphic vector commitment can be simulation extractable. The reason is simply that whenever we give an equivocal commitment to the adversary can then do a linear combination of this equivocal commitment and a different commitment, and it gets a new commitment. But from this new commitment, we cannot extract because it doesn't have a well-defined value anymore, because we used an equivocal commitment to produce it, essentially. And so there is no defined value, so you cannot extract. So that's bad, but the good thing is that technically we don't need the full thing to be linearly homomorphic. We do not need the commitments to be aggregatable. We only need the openings to be aggregated. So the idea is that we could break the homomorphism of the commitments, but retain the homomorphism for the openings. So how might we be able to do that? Well, so we construct a simulation extractable vector commitment scheme from KCG by basically doing the following. To commit to a vector x of length L, normally in KCG, you would now essentially take the unique polynomial f that corresponds exactly to this vector, the unique polynomial of degree L minus 1, and commit to that. But instead, what we're doing is we're taking a larger degree polynomial. Specifically, we take a L plus 1 degree polynomial. And we choose a random polynomial f of degree L plus 1, such that, there's a typo here, there should be an I. Basically, it is consistent with the vector on the positions 1 through L, but otherwise it is completely random. So it is now no longer fixed completely by the vector, but it has 2 additional degrees of freedom. So why do we do that? Well, we now commit to this polynomial, and then we derive a point Z0 as the random oracle applied to the commitment itself. So what we get from that is a random point, and we now open the commitment at this random point and publish as our full commitment the KCG commitment, as well as the value at this point and the opening. Now, this is helpful because it means that we can now verify that commitments are well-formed. This means whenever you see a commitment, you can just rederive Z0, and you can verify that the opening that is part of the commitment is correct. And this means we break the linear homomorphism, because now whenever an adversary tries to basically produce a new commitment based on commitments it has seen, well, because it's a new commitment, that means the Z0 will be different for it with overwhelming probability, which means it would need to open a commitment at a new point, but it doesn't have the information that would be required to do the opening. So that means it's basically not possible for an adversary to actually construct new commitments from old commitments. And this basically allows us to then prove this simulation expectability. So openings for this commitment are basically just openings of the underlying KCG commitment, and you can aggregate those exactly as I said before. We basically derive such a weight C. It's derived from a bit different values here, but it's basically the same idea. So we derive this value, and then we compute this linear combination of all of the openings, and this is your aggregated opening. And the aggregated openings can be verified using the linear homomorphism of KCG. Basically, you can individually verify that all of the commitments are well-formed, and then you can rederive the Xi, and then you can compute the linear combinations of the X's and the commitments, and then you can just verify this opening of the normal KCG. Yeah, so, and this basically now allows us to prove a simulation expectability for this vector commitment. I will not have time to go through any part of the proof, really. Neither will I be able to even describe the definitions that we have. However, we have some comparison with the VRF-based lottery that is currently in use. So basically, we can see that already for relatively modest sizes of the committee, our scheme is much, much smaller. So basically, which is not very surprising. In our case, the aggregated ticket is basically always 80 bytes, whereas obviously, if you cannot aggregate them, it just grows linearly in the number of tickets. So if you get to something like 2,000 tickets, it's already like 3 orders of magnitude larger to store all of these tickets instead of doing the average. Now, one might think that maybe you have to pay for this with additional runtime during verification, but this is not the case. Verifying our aggregated tickets is actually faster than verifying the VRF-based lottery tickets. So what takes a bit of time, of course, which is not something that you need to do with the non-aggregatable one, is actually aggregating them. But there, even for like 2048 tickets, aggregating them only takes 14 milliseconds. So for almost all applications, that should be faster. Yeah, and with that, I am done. And thank you for your attention. And I'm happy to answer any questions.
So is there any question to Niels?
Hello, thanks for a nice talk. So sorry, I have a question. If the only issue is with the storage of this Sweden ticket, so
Could you
yes.
speak up a bit?
yeah. I mean, if the only issue is with the storage of these winning tickets, why don't you just, for example, use an accumulator for all of these winning tickets and then store the accumulation value and then use some, for example, data availability layer for the actual stuff? Why prevent you to use that? Or what's the issue with this approach? Instead of using a new VRF, you have all of these winning tickets and then use them in an accumulator to accumulate all of them so that you store the accumulated value. And then you can query, for example, anytime you want. If the only issue is with the storage and with the motivation is to
You want, I'm not sure I understood your suggested solution. So you want to aggregate the
No, we have all of these winning tickets, okay. Because of the storage, we don't want to store all of them. So we store an accumulation of all of these winning tickets. And then we use a data availability layer or whatever if the actual ones are needed somewhere. And then, so this is, we also have an accumulated value to as a representation for all of these winning tickets.
I mean, it's not clear to me how you would accumulate those in a way that you can then still individually verify.
Okay, so you want to actually you want to be able to verify them
So the
simultaneously.
important point is that anybody needs to be able to verify who won the lottery.
Okay.
This is important because this committee then makes some kind of decision, and you need to be able to check that the correct participant basically made that decision. So you need to check that indeed the selected committee made that decision. So that means that you need to be able to verify that which participants will basically in there.
Okay.
And I'm not sure how you would do that.
Thanks.
We think, is there any more question? If there is no, yeah, thank you for your talk again. When we will start the final last talk. So can you share the screen, Fatima?
Sure.
Yeah, great. So our last talk is early stopping Byzantine agreement in the 1 plus epsilon times F round. And the speaker is Fatima Eshmai, and there are Julian Ross and Chara Lampos, Papamantos are the co-authors. And yes, please start.
Hi, everyone. So today I'm going to present early stopping Byzantine agreement in 1 plus epsilon F rounds. So we start with the definition of the Byzantine agreement problem, where you have n parties. Each party has an input and parties try to agree on a common output. So Byzantine agreement guarantees validity such that if every honest party has value V, then all honest parties output V. And it also guarantees agreement such that all honest parties output the same value. In our work, we assume synchronous setting such that there is a known upper bound on the message delivery delay. For example, if a party sends a message in the beginning of the round, then you expect parties to receive it by the end of this round. And we also assume an honest majority setting such that the adversary can corrupt up to T less than n over 2 parties. So in this work, we are mainly concerned with the round efficiency of the Byzantine agreement protocols. There is a known lower bound for the round complexity by Dollar-Vreshuk and Strong, such that the lower bound is minimum F plus 2, T plus 1, where here F is the exact number of corrupted parties during an execution, and T is an upper bound on the resilience that the protocol can withstand. So in this work, we propose two protocols, a deterministic version and a randomized version. So for the deterministic version, there has been a lot of recent work that's trying to achieve this optimal lower bound in different resilience settings. So our work is for the t less than n over 2. For the t less than n over 3, there's already an optimal solution by Itai, Abraham, and Dolib. For our work, we improve over the work by Perry and Tuig in 1988, where they have around complexity of minimum 2f plus 4 2t plus 2, which basically a factor of 2 more than the optimal lower bound. For our protocol, we have around complexity of 1 plus epsilon f, where epsilon here is strictly less than 1. So our leading factor is strictly less than 2, and this is why it is an improvement over Perry and Tuig. For our randomized protocol, our work improves on the work of Goldrich and Petrank in 1990, where they have a constant expected complexity, but they have a worst case complexity of t plus log t, compared to our work where we have a worst case complexity of 1 plus epsilon f. So here we adapt the worst case complexity, the exact number of corruption, compared to them where they just use the upper bound t. So to go over our construction for the deterministic Byzantine agreement, our starting building block is basically a method to detect malicious parties. To do so, we use the correct or detected broadcast by Fitzy and Nelson, where basically this is a shorter version of Dolby-Strong. So here, this is a broadcast protocol. So here you have a sender with an input, and parties output a value in 0 or 1, a flag C or D, where C stands for correct and D for detect, and the output FI, which is a subset of parties that they think they are malicious. So this protocol runs for D plus 4 rounds. D here as a predefined constant, so the protocol runs in constant number of rounds. Informally, the protocol guarantees that parties either have agreement and hence correct, or if they do not have agreement, then all parties identify at least the same D malicious parties, which is detect. So if a party outputs flag C, then it knows it's in the correct view and parties have agreement. If it outputs a flag D, then it knows that parties detect the malicious parties, but it is not sure whether they are in agreement or not. Our next building block is a way to restrict those detected parties. So it is called a proof participation protocol, which is just a one round where basically each party sends an honesty message to parties not in its faulty list. So basically it is attestation to their honesty. And by the end of a round, if a party collects at least n over 2 honesty messages, then it can form what we call a proof of participation, which is basically a proof of its honesty to continue participating in the next protocols. So our third building block, it is just a combination of the first and second building block, where parties start with the proof of participation to collect this validity proof of their honesty, and they use this proof to then play in the correct or detected broadcaster protocol. So the output is similar to the output of the correct or detected broadcast protocol, and the protocol in general does guarantee the same security properties as the correct or detected broadcast protocol. The only difference here is that only parties with the valid proof of participation that they can participate in the correct or detected broadcast. And since the proof of participation is just one round and the correct or detected broadcast is D plus 4 rounds, then you have a total of D plus 5 rounds. So our fourth building block is called one-graded D-detecting agreement, which basically a flavor of graded agreement protocols, but here we improve on it that if parties do not have agreement, then they do detect the D-malicious parties. So to achieve this, each party sends or like runs an instance of pi DCOD using as an input their initial value. And then based on the output of all the instances of the pi DCOD protocols, they decide on the output. So it is basically a deterministic function over all the output of the n instances of the pi DCOD. And based on that, they output a value and a grade in 0 or 1. So informally, the protocol guarantees that if all honest party input the same value, then they all output this value and grade 1. So they know they have agreement. And if an honest party outputs a grade less than 1, then all honest party detect D-malicious parties. And then since the protocol just run pi DCOD and we don't really run any more rounds, so the overall complexity just follows from the complexity of the pi DCOD, and then you have here the D+5 round complexity. So to form the Byzantine agreement, we use the graded detecting agreement protocol. So the Byzantine agreement protocol runs in iterations, where basically in each iteration, parties run the 1GDA protocol. And then based on the output of this protocol, they decide whether it is safe to terminate in this iteration or will they have to go to more iterations till they reach agreement. So in case it's not safe for you to terminate, then you run another instance where the input to your new iteration is basically the output of the previous iteration, the grade agreement protocol. Otherwise, just terminate and output the value of the grade agreement protocol. So from the properties of the grade agreement protocol, it detects D-malicious parties per run. So the number of iterations to eliminate all malicious parties is going to be f over d. And since in GDA, parties like run POP as a subroutine, once you detect and eliminate the malicious parties per iteration, they cannot participate in the next iterations because they will not have a valid POP. So now the overall round complexity of the protocol is D+5 times f over D+2. So D+5 is because the graded agreement protocol is D+5 rounds. The f over d is because it takes f over d iterations to eliminate all malicious parties. And then you need 2 more iterations to basically get parties to agree. So the reason for this is that after you eliminate all the f malicious parties may start the next iteration with different input values. So if parties have different input values, you are not sure they are going to output grade 1. So you need 1 iterations for all parties to agree on the same output. And then in the second iteration or the last iteration, they're all going to have the same input, and hence you ensure that all parties are going to output the same value with grade 1 in this last iterations. And this is the reason for why you need extra 2 more iterations. So overall, you have like D+5 over D factor over in front of F, so it is less than 2. So this is the construction for the deterministic version of the Byzantine agreement. So now for the randomized version, we use the building blocks from before to construct the randomized Byzantine agreement. So again, we start with the pi1GDA protocol to form a 2-graded detecting agreement. So it is just boosted grades basically. So after you run the pi1GDA, you input your output to some 4 rounds of protocol. We call it grade booster, where basically it boosts your grade from 0 and 1 to 0, 1, and 2. So the guarantees for the protocol is similar to the one graded detecting agreement protocol. It's only difference on the grading you output. So again, we ensure that if all honest parties input the same value, they all output V and grade 2. And if an honest party outputs a grade less than 2, so here the party is not sure whether they have agreement or not, it ensures that all parties detect the same D-malicious parties. So for the round complexity from before, the pi1 GDA has D plus 5 rounds, and the grade booster is 4 more rounds. So in total, you have a D plus 9 round complexity. So to form the Byzantine agreement, the randomized version, it again follows a similar notion to our deterministic version. So in each iteration, you start by running the pi2 GDA protocol. And then again, you look at the output and you see whether it is safe to terminate or not. The difference from before is that here, you don't just input to the next iteration the output from your previous one. It will depend on your grade. So if your grade is at least 1, then you use your output from before. But if your grade is 0, then you use a common coin. So assume here we have some strong common coin that with some probability P, all honest parties will receive the same value from the common coin. So here the expected round complexity is constant because with some probability, you ensure that all parties are going to have the same input to the next iteration. And once this happens, you know that parties are going to terminate in this iteration. And for the worst case complexity, it follows the same way from before, where you need f over d iterations to eliminate all the f parties, and then you need 2 more iterations for agreement. And since the pi2GDA protocol has d plus 9 round complexity, then the overall worst case round complexity is d plus 9 times the number of iterations needed. And yeah, that is our presentation. Thank you.
Thank you. Thank you for the nice talk. And is there any question? Okay, so thank you again for the presentation. I have a question. So I'm curious about whether is your technique possible to extend to like some other setting, for example, like F plus constant round or like dishonest majority? Do you think is it possible?
No, it will not work for this honest majority setting. Because our grade agreement protocol or all the smaller building blocks are mainly for the T less than n over 2 setting. So it's not really straightforward to extend it to the T less than n, because we need some kind of majority, or even for the proof participation, you need the at least n over 2 such messages. So like you depend on the majority to have agreement and the protocols basically.
I see. How about make epsilon equal to this 0 also 0? Like optimally linearly depends on F. Is that possible?
So we have the D, the predefined constant D, and this is why we have the epsilon. So if you want to really reduce the epsilon a lot, you're going to increase the D, like to very high D. So which still bad, because then it means the first iteration is going to be a huge number, because the first iteration takes D plus 5 rounds. So if you increase the D a lot and then you have a small f, then you are not really doing anything. You're ruining your round complexity. So you need to have some kind of sweet spot between the value of D and the value of F, like of the exact number of corrupted parties, basically.
Okay, thank you very much.
Thank you.
Yeah. Yeah. Thanks again, Fatima.
Thank you.
Thank you all for participating in Asiacrypt. So this is the end of our conference. please enjoy the last chat with our colleague. Thank you all.